In 1907, something was different. A silent but fast train starts to approach the station. Unlike previous trains, there's no smoke or even sound. The electric revolution has arrived. Over the last 100 years, electric trains have changed in nearly every aspect, from what motors are going to be used to how powerful they've become and how it's impacted the world around them. My name is Jamie, and I'm here to tell you all about how they evolved and changed. Some of the most famous of these engines would be the famed Pennsylvania Railroad GG1, New Haven's EP4, or the modern-day Siemens ACS 64. The focus on this series is on 5 railroads: the Pennsylvania, the New Haven, the New York Central, their successors, Amtrak and Penn Central. In today's episodes, we focus on the New York, New Haven and Hartford Railroad, and how they pioneered electric locomotives. If you are interested in further history of electric locomotives, do subscribe and like this video. It does help a lot, and I will be doing further episodes of this fortnightly. We do alternate between passenger trains and the electric videos, so be excited. The New Haven Railroad was truly a pioneer. They had to figure out everything: how the catenary was designed, the type of power, even the generators used. We take it for granted today, but somebody had to figure it out. The New Haven established single-phase AC current as a possible and economical competitor to DC power. While New Haven didn't first try out AC but DC, we'll first explore their options. The New Haven Railroad had multiple experiments trying out early electrification. In 1895, the first attempt at overhead electrification was from Nantasket Junction to Pemberton using 600 to 700 volts DC. This was 6.8 miles long initially, but was later extended by 3.5 miles to East Weymouth in 1896. New Haven would also try out third rail electrification, and this was between Hartford, New Britain, and Berlin. This system was about 12 miles in length, and unlike the normal top or bottom running explained in the New York Central video, the third rail was mounted in between the rails, similar to as simple as it can be, the Lionel trains. It was also exposed to the elements, and because of this, many accidents occurred. This system would also be forbidden due to accidents occurring at drastic rates, and on June 13, 1906, it was deemed forbidden by the Connecticut Supreme Court. This eliminated an option for New Haven. Wanting to electrify further, they had to choose either DC overhead or AC overhead. AC single-phase electrification was a relatively new concept at the time. There were a few 3-phase electrification schemes in Europe, but these were the exception to the rule, and were kept separate from steam locomotives. At this time, using a DC system was only seen as 75% efficient according to the efficiency plans. An alternative was given by Westinghouse, who had been researching AC electrification since 1895. One advantage of AC versus DC is simply cost. DC may have a lower initial cost compared to AC due to simpler equipment. However, a factor at that time was the reduced instances with DC overhead. This meant it would require more substations compared to AC overhead. The New Haven Railroad had to make educated guesses, as this system was the first to have steam and electric locomotives functioning at the same time. It also meant that they had no one else to rely on when creating this new system when it came to practical experience. AC power has multiple advantages over conventional DC power, and eventually they would choose 11 kilovolts, 25 Hz single-phase AC current as a way to electrify the railroad. At the time, the highest voltage produced by generators was 22 kilovolts. This was then to be transformed to a 6 kilovolt line voltage, and then transformed on the locomotive at a voltage of 560 volts. To save money and to be more efficient, 11 kilovolts was chosen as a halfway to illuminate the immediate transformer. A solution to even make it more efficient was the removals of transformers altogether, as choosing 11 kilovolt generators would be selected, as it could be linked directly to the system without requiring a transformer, and it would be now stepped down on the locomotive itself. Another question that we should ask is why 25 Hz? To explain as simple as possible is due to multiple factors. Lower frequency has two separate advantages. One is that we get less resistive loss in power over longer distances, and it also becomes much easier to control universal motors with tap changes. A tap changer is a part of a transformer that allows the output voltage of a transformer to be changed. Also, the reason for 25 Hz specifically is due to rotary frequency converters being more efficient at lower frequencies. A lack of small control equipment and rectifiers at the time stopped the move to higher frequencies. These days, locomotives either use chopper control units or variable voltage, variable frequency to control the traction motors these days. Most railways now are shifting towards 50 Hz or 60 Hz due to the commercial standard being 60 Hz in America and 50 Hz in Europe. Amtrak at the moment is one to convert a lot of the ex-Pennsylvania Railroad and New Haven to its new frequency, 60 Hz. However, due to issues with clearances in places with low bridges and small tolerances within tunnels, it is facing a lot of difficulty. It was first decided that its main line from Woodlawn, New York to Stamford, Connecticut would be initially electrified. However, there were strong hopes to electrify all the way to Boston. This would never surface, and the electrification scheme would only reach New Haven. Two factors must be considered of why this decision was made. Changing from electric to steam traction takes time, and space to do so on a heavy main line would cause congestion and cause delays to commuters and to other passing trains. It was decided that the trains would change over at the end of the suburban zone, hence the decision to end the electrification at Stamford. An advantage of electrification was, from New Haven's point of view, was that it could allow for extra capacity on the 4 tracks main line without requiring more tracks to be built. An advantage of electric trains in general is the acceleration, meaning that it was able to reach its top speed quicker and easier compared to steam traction at the time. One problem faced with the first days of electrification was one simple thing: power. Electric railways require a lot of power. However, at this time, the commercial grid was only starting to take off, and the power needed to power the new railway wasn't there. Therefore, New Haven had to build its own power plant dedicated to the railroad. A new plant at Coscob, Connecticut was built. These had 3 steam turbines connected to 3,000 kilowatt generators, and another was added after the first 3 were installed. They would produce this power at 11 kilovolts, therefore skipping the need for a transformer, and could be directly connected to the overhead system. In 1905, the first prototypes for electric locomotives on the New Haven Railroad would arrive on the scene, EP4. These were truly a genesis for what was to come, as these would be equipped with a DC pantograph, an AC pantograph, and a third rail chute. Designed to go into New York Central trackage as well, it also meant that it had to be third rail compatible. The EP1 was of a box cab design and used a gearless drive system like on the B&O's 1895 electric locomotives. The EP1 was more sophisticated than the electrics on the New York Central, due to the EP1 using the gearless quill drive, which allowed the weight of the motors to be borne by the truck frame itself. Despite the boxy look, the EP1 could exceed speeds of 80 miles per hour and could reach 89 miles per hour in tests. One thing that New Haven pushed, and would become the first railroad to do so in regular use, was multiple unit control on locomotives. While the New York Central units were able to do so, it was rarely done compared to the New Haven. The EP1s were truly a marvel to be seen, but they had some issues. The most serious of these issues was called oscillating, and there was also a lack of stability. However, it was also noticed at high speeds that the driving trucks would also oscillate from side to side. This issue was corrected by adding additional non-driving trucks on both ends. And in 1909, the EP1s would average 12,000 miles between locomotive-caused delays. These new trains would usher in a new success for New Haven. The New Haven Railroad would be also handling more than 11.4 million passengers per year into Grand Central. Within a decade, this had increased to 16.3 million passengers. However, this also meant that the trains were getting longer, but also heavier due to the wooden cars now being replaced by steel-bodied cars. By 1910, the plan was deemed a complete success. And while it was only intended to ever have electric passenger trains, it would choose to electrify its freight operations and its switcher units. Westinghouse would simply modify the EP1 design for freight, changing the gearing to 45 miles per hour top speed, while removing passenger-focused equipment such as heaters. Something that may surprise you is the removal of third rail equipment, as this was generally only needed for passenger trains, which needed them to traverse into Grand Central. As the Hell Gate Bridge route opened in 1918 to electric locomotives, more locomotives would be needed. Despite having tried some disappointing prototypes from General Electric, New Haven would return to Westinghouse for an improved version of the EP1. Instead of having a 1B1 configuration like the previous EP1, EP2 would have a 1C1 plus 1C1 configuration. This meant that it would have more driving wheels and basically be more powerful. And in 1933, as the Pennsylvania Railroad replaced the 600 volts DC third rail with 11 kilovolts overhead AC, this would allow for New Haven's electric locomotives to operate into Pennsylvania Station and eliminate engine change in Queens. General Electric would have a second chance at convincing New Haven with its EF2 locomotives. GE would build 7 of these EF2s. These were 1B1 locomotives. However, these locomotives were very different as they would be equipped with DC traction motors. EF2 would have a motor generator set within the car body. This would convert the 11 kilovolts AC to DC current and would provide the low voltage for the DC traction motors. While the EF2 was kept in service for more than 2 decades, the motor generator concept would not continue with the later EP3 and EF3 locomotives. The final locomotive we will discuss is the EP3, the precursor to the Pennsylvania Railroad GG1. The EP3 would be built by General Electric, displacing Westinghouse as the go-to locomotive builder for the New Haven Railroad. General Electric would build 10 EP3s in 1931, using a 2C plus 2C configuration at GE's Erie plant. EP3s were given the road numbers from 0350 to 0359. The 0 is important to remember as the numbering scheme for the New Haven will give all non-steam locomotive at the time a 0 indicating other than steam. The EP3 would have a combined rating of 3,440 horsepower with 68,500 pounds of tractive effort. They would also have a space speed rating of 80 miles per hour, and the EP3s would be more known for the contribution to the development of the iconic GG1. In the previous episode, I talked about how the Pennsylvania Railroad P5A was struggling on heavier runs and a solution was needed. Well, EP3 0354 would be used as a comparison to the P5A as a way to figure out what the replacement was going to be. The EP3 would track incredibly well and would be eventually used as the basis for the GG1 design. Today, that's all we will cover. Next time on this topic of electrifying the East Coast, I will discuss about the New York Central, how it continues its electrification project, and I will also be exploring the Pennsylvania Railroad's Broadway Limited next week, and how to model that train while explaining the history behind that incredible train. Thank you for watching this episode of Pan Up, a series of where we explore the history of East Coast electrics. And don't forget to subscribe and like this video, as it does help me out in getting these videos to more people. I just want to say thank you to my viewers and to my partner for supporting me. So I hope you enjoyed this Christmas, and I wish you a happy holidays as we slowly draw our way towards Christmas.